topics, the atomic structure. An atom is the smallest unit of matter that retains all of the chemical properties of an element.
An atom is composed of two regions, the nucleus, which is in the center of an atom and contains protons and neutrons, and the outer region of an atom, which holds its electrons in orbit around the nucleus. Atoms consist of three basic particles: protons, electrons, and neutrons. Protons are the positively charged subatomic particle forming part of the nucleus of an atom and determining the atomic number of an element. The outermost regions of the atom are called electron shells and contain the electrons negatively charged.
So the next topic is all about accuracy and precision. So, what are accuracy and precision, by the way? Accuracy is how close a measurement to the target value, while precision is how consistent the results are regardless of the proximity of the target value.
We assume that three darts are thrown at the dartboard, with the bullseye representing the true or accepted value of what is being measured. A dart that hits the bullseye is highly accurate, whereas a dart that lands far away from the bullseye displays poor accuracy. This figure demonstrates four possible outcomes. The darts have landed far from each other and far from the bullseye. This grouping demonstrates measurements that are neither accurate nor precise. The darts are close to one another but far from the bullseye. This grouping demonstrates measurements that are precise but not accurate. In the laboratory situation, high precision with low accuracy often results from a systematic error. The darts are not grouped very near to each other, but are generally centered around the bullseye. This demonstrates poor precision but fairly high accuracy. The darts are grouped together and have hit the bullseye. This demonstrates high precision and high accuracy. Scientists always strive to maximize both in their measurements.
Our topic is about nomenclature, or in simple words, the system of naming compounds. The first thing is binary compound. There are two ways in naming binary compounds. The first is the reaction between metal and nonmetal, and the second thing is the reaction between nonmetal and nonmetal. For binary compound, it follows the stock system. The parenthesis contains a Roman numeral, and the Roman numeral represents the charge of the metal, and write the stem name of the anion, then add IDE. For example, calcium and oxygen, it will become calcium oxide. You can also use the suffix OUS or US and IC or IC. It can be used to distinguish the two different charges. The metal with lower charge uses US. The metal with higher charge uses IC. For example, iron has two charges, 2 and 3. First, iron 2 oxide or ferrous oxide. Second, iron 3 oxide or ferric oxide. For binary compound nonmetal and nonmetal, write the name of the first element and write the stem name of the second, but with addition of still IDE. Use proper prefix to signify the number of atoms of the elements in the compound. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. For example, CO or carbon and oxygen results to carbon monoxide, CO2 or carbon dioxide, and to O5 or dinitrogen pentaoxide. Second is ternary compound. It is naming for the polyatomic ion or the oxyanion. For ternary compound, write cation first followed by the anion. If an ion is monoatomic ion, add IDE. One with fewer oxygen atom, ends with ITE. Higher or more oxygen atom ends with ATE. For example, MgCO3 equals to magnesium carbonate. Na3PO4 equals to trisodium phosphate. Prefix can also be used in ions, hypo for lower and per for higher. For example, BrO4 results to perbromate. BrO results to hypobromite.
Given the equation CH4 plus Cl2 produced to CCl4 plus HCl. To balance this equation, first is count the number of atoms on each side of the equation. You can only change or add coefficients while balancing chemical reactions, never the subscripts. In the reactants, carbon is equal to 1, hydrogen is equal to 4, and chlorine is equal to 2. While on the products, carbon is equal to 1, hydrogen is equal to 1, and chlorine is equal to 5. We can see that this equation is not balanced. In order to be balanced, we will put coefficient 4 in the Cl2 and coefficient 4 in the HCl. So now, carbon is equal to 1, hydrogen is equal to 4, and chlorine is equal to 8.
The last topic is the 5 different gas laws. First gas law is the Boyle's law, a law that describes the relationship between pressure and volume. This law was formulated by an Irish scientist, Robert Boyle, in the late 1600s. He said that when the pressure of a gas increases, the volume of a gas decreases if we assume that the temperature and the amount of gas is constant.
A balloon is filled with helium to a volume of 13.6 liters at a pressure of 101 kilopascal. If the pressure decreases to 35 kilopascal, what is the new volume of the balloon? Assuming temperature is constant. The given are P1 equals 101 kilopascal, V1 equals 13.6 liters, and P2 is equal to 35 kilopascal. Since the pressure is inversely proportional with volume, the formula of this law is P1 times V1 equals P2 times V2. But since we will find the volume 2 of the problem, the formula would be volume 2 is equal to P1 times V1 all over P2. Multiply 101 kilopascal to 13.6 liters divided by 35 kilopascal. The answer would be 39.2 liters, which is now the second volume.
Next gas law is the Charles law, a law that describes the relationship between volume and temperature. This was formulated by a French chemist, Jacques Charles, in the late 1700s. He said that when the temperature increases, the volume also increases.
Calculate the volume of 23.4 liters of air if the temperature is increased from 298 Kelvin to 355 Kelvin. Since volume is directly proportional with temperature, the formula of this law is V1 over T1 equals V2 over T2. Since we are looking for volume 2 or V2, so the formula would be V2 is equal to V1 times T2 over T1. The given are V1 equals 23.4 liters, T1 is equal to 298 Kelvin, T2 is equal to 355 Kelvin. Multiply 23.4 liters to 355 Kelvin divided by 298 Kelvin, the answer would be 27.9 liters, which is now the second volume.
This law was formulated by a French chemist, Joseph Louis Gay-Lussac, in the late 1800s. He said that when the pressure of a gas increases, temperature also increases.
An oxygen tank has a pressure of 1200 kilopascal at 298 Kelvin. What will be the pressure if the temperature is increased to 387 Kelvin?
The given are P1 is equal to 1200 kilopascal, T1 is equal to 298 Kelvin, and T2 is equal to 387 Kelvin. But since you are looking for pressure 2, the formula would be pressure 1 times temperature 2 all over temperature 1. Multiply 1200 kilopascal to 387 Kelvin divided by 298 Kelvin, which is equal to 1560 kilopascal, or the pressure 2. The next law is the Avogadro's law, a law that describes the relationship between the amount of gas and the volume of gas. This law was formulated by Amedeo Avogadro in the late 1800s. He said that when the amount of gas increases, the volume also increases. A balloon is filled with 0.340 mole of air to a volume of 7.60 liters. What will be the volume if the amount of air is increased to 1 mole? The given are N1 is equal to 0.340 mole, V1 is equal to 7.60 liters, and N2 is equal to 1 mole. But since we are looking for volume 2, the formula would be volume 2 is equal to volume 1 times N2 over N1. Multiply 7.60 liters to 1 mole divided by 0.340 mole, which is equal to 22.4 liters, or the second volume. And the last law is the ideal gas law, the combination of the 4 different gas laws. A weather balloon is filled with helium to a volume of 84.6 liters at 25 degrees Celsius and 101 kilopascal. If the balloon rises to an altitude where the pressure is reduced to 30 kilopascal and the temperature is negative 45 degrees Celsius, what is the new volume? Since this law is a combination of all the gas laws, the formula of this law is equal to V1 times P1 over T1 equals to V2 times P2 over T2. The given are V1 is equal to 84.6 liters, T1 is equal to 25 degrees Celsius, P1 is equal to 101 kilopascal, P2 is equal to 30 kilopascal, and T2 is equal to negative 45 degrees Celsius. Since the given temperature is in degrees Celsius, we should convert this to Kelvin. Temperature 1 is equal to 25 degrees Celsius plus 273 in order to become 298 Kelvin, and temperature 2 is equal to negative 45 degrees Celsius plus 273 in order to become 228 Kelvin. Since we are looking for volume 2, the formula would be P1 times V1 times T2 all over T1 times P2. Multiply 101 kilopascal to 84.6 liters and to 228 Kelvin divided by 298 Kelvin times 30 kilopascal. The answer would be 218 liters, or the second volume.